Welcome to this exploration of one of the most fascinating concepts in physics, wave-particle duality of light. For centuries, scientists debated whether light is a wave or a stream of particles. The surprising answer is that light behaves as both, depending on how we observe it. This dual nature revolutionized our understanding of physics and led to the development of quantum mechanics. In this video, we will explore how light exhibits both wave properties and particle properties, and why this matters. Let's start by looking at light's wave properties. When light behaves as a wave, it demonstrates several characteristic behaviors. First, it creates interference patterns when waves overlap, similar to ripples on water. Second, it exhibits diffraction effects, bending around obstacles and spreading through openings. Third, light can be polarized, meaning its wave oscillations can be oriented in specific directions. Finally, as a wave, light has measurable wavelength and frequency. These wave properties were well established through numerous experiments in the 18th and 19th centuries. The wave nature of light is mathematically described by a fundamental equation, c equals lambda nu. Here, c represents the speed of light, which is approximately 3 times 10 to the power 8 meters per second in vacuum. Lambda, the Greek letter, represents the wavelength, which is the distance between consecutive wave peaks. Nu, another Greek letter, represents the frequency, which is the number of wave cycles passing a point per second. This equation shows that the speed of light is the product of its wavelength and frequency, and it remains constant in a given medium. Now let's examine light's particle properties. When light behaves as a particle, it exists as discrete packets of energy called photons. The photoelectric effect, which we'll discuss in detail shortly, demonstrates this particle behavior beautifully. When light interacts with matter, it transfers energy in discrete amounts rather than continuously, supporting the particle model. Another phenomenon called Compton scattering shows that photons can collide with electrons like billiard balls, further confirming light's particle nature. These particle properties couldn't be explained by the wave theory alone. The energy of a photon is given by the equation E equals h nu. Here, E represents the energy of a single photon. The letter h stands for Planck's constant, a fundamental constant in quantum mechanics with a value of 6.626 times 10 to the power negative 34 joule-seconds. Nu represents the frequency of light. This equation tells us something profound. The energy of a photon is directly proportional to its frequency. Higher frequency light, like blue or violet, carries more energy per photon than lower frequency light, like red or infrared. The photoelectric effect was the key experiment that revealed light's particle nature, and it earned Albert Einstein the Nobel Prize. Here's what happens. When light shines on certain metal surfaces, it ejects electrons from the material. But there are 3 surprising observations. First, the effect depends on the frequency of light, not its intensity. Even very bright red light might not eject any electrons, while dim ultraviolet light does. Second, the electron emission is instantaneous. There's no delay, even with very low intensity light. Third, increasing the light's intensity increases the number of ejected electrons, but not their energy. These observations contradicted the wave theory, but were perfectly explained by Einstein's photon model. The double-slit experiment beautifully demonstrates both wave and particle aspects of light simultaneously. When light passes through 2 narrow slits, it creates an interference pattern on a screen behind them, showing alternating bright and dark bands. This is classic wave behavior. However, if we detect individual photons, we find that each one arrives at the screen as a discrete point, like a particle. Even more mysteriously, if we try to observe which slit each photon passes through, the interference pattern disappears. The act of observation changes the behavior from wave-like to particle-like. This experiment shows that light exhibits both behaviors, but never both at the same time. So what's the key takeaway from wave-particle duality? Light exhibits both wave and particle properties depending on how we observe it. It's not that light is sometimes a wave and sometimes a particle. Rather, light has a dual nature that encompasses both aspects. When we set up experiments to detect wave properties like interference, light behaves as a wave. When we set up experiments to detect particle properties like discrete energy packets, light behaves as particles. This complementary nature is fundamental to quantum mechanics and applies not just to light, but to all matter at the quantum scale. Wave-particle duality reminds us that nature at its most fundamental level is far stranger and more wonderful than our everyday experience suggests.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.